Hi, I'm Lane from Cisco. In this video, I want to talk about RFC2544 again. This is the second part of a two-part series. And what is going to be different as we get into higher performance chips. So in the 4, 5, 6 terabit plus range, and we go all the way up to 25.6T right now is what's shipping. There have been multiple 51.2 terabit devices announced, so that's the next generation that we're kind of coming into. What are some of the differences in what these 2544 reports will look like in this case? And we'll see, don't fear the sawtooth. That's what we're going to get to at the end. Okay, so as I mentioned, this is part of a two-part series. It's important to watch the first part first. What we're looking at here is what are the differences in what those test reports will look like and why for newer chips. Okay, the new limitations we're going to see are going to come from internals inside the device, specifically around bus bandwidth. So explain why that happens and what are the results both on a lab test, but also when we look at real world performance. And of course, we're going to see that our chips and other chips that I work with, while they may see what looks different than you're used to in a lab test, they're not going to have this type of issue become something to worry about in the network. So where do we leave off? This is an example of a real line card of ours. It's one of our 14.4T, so 36 by 400 gigabit Ethernet line cards. And so this is the start of the performance test result. And what you see here is that when we start with 64-byte packets, when we start with 64-byte packets, we get about 42.8% throughput. And so this is pretty common. We're not designing for 64-byte packets anymore. That used to be a big goal of many people. And then over time, we realized that packets and networks were much larger, and the cost of designing a 64-byte line rate caused us to either have much higher power or to give up on bandwidth. And so that's kind of where we start. And then you'll see that as the packets get larger, the throughput increases. And so at this point in the test, the packets per second lookup engine is what's causing limitation. So we have a fixed number of frames per second happening, but because the packets are larger, we have more throughput. And so that's what you can see in this part of the result. And so what's going to happen is, as the packets get larger, eventually we get to a no drop rate, a no drop packet size. And so here you can see that it's at 176, so either 175 or 176 byte. This is only done every even packet size. Eventually we get to full line rate. And you'll notice that we have 99.99 rather than 100%. The reason for that is that if you run 100%, you can get packet loss due to things like synchronization on the interfaces or little things like that, interframe gaps, etc. And because a single frame lost will cause RFC2544 to move to a different test case, we run close to, but not all the way to the limit. Okay. And so in this test, this is what we saw at first. So as the packet sizes became larger, the throughput goes up. And then once we reached the 99.99%, we saw that we maintained that for the rest of for the subsequent packet sizes. And you see that this is going flat. We'll later on see that there's actually something happening above the line, but we can't see that because this is as fast as the interfaces can go. So then the question becomes, what's next? This was, I think about 176, maybe this is 200 something. So what's next? And that's what I want to talk about today. Okay. So the first step is to kind of understand what is happening inside the router. And there are going to be things that are constraints that we optimize around or that we accept. And I want to show you, kind of start by looking at what are the packets that we might be sending through. So the most common packets out there today are really we call a 64-byte packet, which is really a 64-byte frame. There's often some amount of 512 bytes, lot of 1500 bytes, which is kind of the largest packet that you can assume will be handled on Ethernet or on the internet, as well as 9,000 byte packets, which would be called a jumbo frame. That's what would be sort of, you might build that capability into your network for even more efficiency. So what we traditionally call a 64-byte packet is really a 64-byte frame. This will commonly be a TCP acknowledgement. So we're sending lots of data in one direction, maybe from Netflix or YouTube to your phone or to your set-top box. So big packets of video. We have to send some amount of traffic back, or the client has to send some amount of traffic back just to acknowledge that, slow down, speed up, stay the right speed. I've gotten these packets, please retransmit something. So those TCP acknowledgements are in the L4 header. We also have a 20-byte L3 header. There's an 18-byte of overhead and Ethernet, 14 in the header and 4 in the trailer. And so with all these present, we still need to have some padding because of the minimum size of 64 bytes. Now, when we get into the router, you're going to not have to carry that, and then you're not going to have to carry that. So inside the router, it becomes a 40-byte packet. Now, similarly, if we looked at a 512-byte packet, now this might be TCP or it might be something else, UDP, just IPv4, etc. You're going to have, again, this 18 bytes, which is going to be dropped before we get to the insides of the router. We then have probably an IPv4 header, might be v6 header, and then the rest of the payload is going to be adding up to to 512 bytes. So this is just kind of what packets look like, and the reason to mention that is that some of the fields that we may see outside the router are not being managed inside the router. Okay. So now why do we see these sawtooths that we're going to talk about? Inside the chip, moving bits around is much faster, much quicker, much cheaper, less power than anything else. So if you imagine there's a continuum, maybe you're moving chips, packet bits, microns inside the chip, or maybe you're moving to the front panel of the system, or maybe you're moving them across the back plane, or maybe you're moving them 100 meters or 1,000 kilometers. There's sort of a continuum, and on the extreme end is moving things inside the ASIC itself. When we do that, we have multiple blocks inside the chip that we're going to be pushing the packet through. So an example here, I have A, B, and C. Let's call this maybe the MAC. Let's call this the IP lookup. And then let's call this the QoS. Doesn't really matter what they are, just that we have some connections between them. And these connections are called buses. And this is just a number of parallel links between, logical links and physical wires between parts of the chip. And this bus bandwidth is something that we have to manage. We have to size it fast enough so that we can get all our data through. We also don't want to oversize it because that's going to have a penalty either for power or for maybe some capabilities that we might have to give up, because it's always, it's silicon gates for everything. So we're going to look at how do things behave as we go across these buses. Okay. Let's, and when a router designer or chip designer builds the device, they have choices of how wide to make these buses, as well as how fast to clock the chip. So let's say you could go 64 bytes or 128 or 192 or 256. So there's all these different sizes you could make these buses, and they all have different trade-offs. So for this example, I'm going to say that we have a 100 byte wide bus. This is not necessarily what we use in the chips that I work with, the Silicon One at Cisco, but it's a nice example. As we move things through these buses, We are therefore going to be doing them 100 bytes in this case at a time. That means that if we have 50 bytes that we're moving, then we're going to, for that clock cycle, be 50% efficient. The other 50 bytes are going to be sort of unused for that clock cycle. If we're at 99 bytes, 99% efficient, 100 bytes, 100% efficient. If we're at 101 bytes, then we're going to be 101 divided by 2 efficient, so about 50.1% or something like that again. So we want to understand how is the data that we are sending through the device map into the bus size that we've chosen. So in this example, again, I'm using a 100-byte wide bus. I'm using a device that happens to have a 30-byte internal header. Again, this is not necessarily a Cisco chip. This internal header is doing things like keeping track of which interface it's going to go out, maybe some internal QoS, things like that, timestamps, etc. So this is something that's going to be prepended to the packet when it's inside the router, and then it's going to be discarded on egress. Okay, so in this packet here, I'm just sending, I'm sending a 64-byte frame or a 40-byte TCP/IP packet that's an acknowledgement. So what we have is, in this 100 bytes, we have 30 bytes of overhead, we have 40 bytes of payload, and then we have 30 bytes of effectively padding or bandwidth that we're not going to use. So for this particular transaction, we have a 70% efficiency. So it's not perfect, it's not bad, it's just kind of in the middle. Now let's take a look at what the most common transfer is going to be inside a chip. So if you look at internet data, which we'll take a little bit closer look at later, you have a lot of the bandwidth at 1500 or 1518 byte packets. And this is the sort of traditional MTU of Ethernet. So we know that anything on the internet is able to support these packets. It's not guaranteed that you can go larger. So often people will just use jumbo frames inside their networks. Okay. So taking 1500 bytes through a 100-byte wide bus is going to look like this. We still have this 30-byte internal header. We put 70 bytes of this packet into that same clock in that same window. And we have then 100% utilization for all the next 14 clock cycles. We then have 30 bytes going in that last clock cycle, and then we have 70 bytes here that's empty. Okay, so what we end up with is 1530 bytes of payload going into, including the header, going into 1600 bytes of max bandwidth available cycles. So we end up with 95.6%. So what this is really showing you is, if you chose any of the block sizes that I mentioned before, 128, 192, 256, 100, most of the data going through the router is these larger packets. And so with any of those sizes, we're going to have lots of them that are 100% full. And it's really only the last one that might have some wasted cycles. And so pretty much any of the choices we have has the ability to be quite efficient. Now let's take a look at the worst case example. And so when we talk about the sawtooth in a minute, this is kind of where the sawtooth would begin. So let's say that I have a 171 byte packet and I'm going over a 100 byte wide bus. So what's going to happen here? Again, we have our header. In the rest of that first cycle, we've got these 70 bytes. We then have another cycle with 100 bytes, and then we have one more byte that we have to send, so we put that into the third cycle. So in this case, we have sent 200 bytes, but we've had 300 bytes, we had 201 bytes, but 300 bytes worth of possible bandwidth. So we did lose, some of this capacity here. If we had a network with nothing but 71 byte packets, that's probably not great, but that doesn't exist, so it's fine. So this is what would be the worst case. Now you may ask why maybe a 71 byte packet isn't the worst case. And the answer is that usually there's going to be another bottleneck, basically the PPS lookup. So we can't get fast enough with 71 byte packets for this to be the constraint. So what does this now look like when we get our RFC2544 report? So let's start with the example we had before. So at 64 byte packets, we were around 42, I think, %. Okay, and then we're going to be, going up. And I think in our example before, it was about 176 when we reached 100%. So this is the no drop rate. And in a minute, we're going to see why we call that the first no drop rate. Okay, and then we had some range here in which we maintained the line rate. And interestingly, what was happening is this is what you would see outside, but inside the router, you actually have some performance that happens faster than what you would see as the external line rate. And this is going to be important. This is called speed up, because so what's happening is even if packets are coming in at, let's say 12.8 terabits, for a certain period of size, you might have 14 terabits capable of moving. So if we have some of those 171 byte packets, but we also have some 1,000 byte packets, those 1,000 byte packets are actually going faster than line rate, so they actually go over speed so they can compensate for the inefficiency of some of the other sizes. Okay, so now what's going to happen is called a sawtooth. So when we get to that, and this 176 bytes, that was from one of our real examples. If we go back to the other example with a 100 byte bus, it was actually around 171. So what's going to happen is in that other example, so this is let's forget about that for a second. This is the 170 is right there. At 171, what we're going to have is some kind of drop. And I may have drawn this a little bit too sharp. Let's go back a bit. But we're going to have some sort of drop, and this represents that inefficiency when we go over the border. Go from 2 cycles to 3, but we only put 1 byte in there. So what's going to happen then is we're going to resume the PPS-driven or the bandwidth-driven climb back to 100%. This would be the second no drop rate. Okay. And then we might have another one. We might even have another one. Depends on exactly what the device looks like. Each of these sawtooths, this is what it's called, this is the sawtooth here. Each of these sawtooths is going to get smaller, and eventually in most devices you would be reaching a line rate. So this is what it's going to look like if you run a high bandwidth chip through RFC2544. You're going to first be PPS limited. You're going to probably reach a line rate. You're going to have a sawtooth in which you drop. You'll come back up to line rate, and so on. It might be 1 sawtooth, it might be 5 sawtooths. It all depends around what you're doing. And then usually by the time you get to 1,500 bytes, you're going to be very efficient. And also remember that above these sawtooths, there's actually periods of extra efficiency that you can use to balance out the times when you're a little bit slower. So even if you sent lots of 171 byte packets, if you also had 1,500 byte packets, those would even out, and you would see that the average packet, you get the kind of the efficiency of an average, and those 171 byte packets would still be getting through. They'd just be a little less efficient. These 1,000 byte packets would be getting through with extra efficiency, and it would all even out. So let's actually take a look at what are the packets that we're actually running through a network. So you can kind of divide into 3 on the IP sort of side. You can kind of divide into 3 main categories. You may have internet, data center, and machine learning. On the internet, and I've got some graphics coming up showing that, but you tend to have TCP acknowledgements, which are a decent amount of traffic by packet but not as much by actual bytes. And bytes are what we care about here. Because those packets are smaller, they're not contributing as many bytes. You have most of the bytes, most of the bandwidth coming through with 1500 byte packets. You also will have, for some legacy reasons, some 512 byte packets, as well as you'll have some number of random sizes which may represent kind of what was left over after I send a bunch of 1500 byte packets, or some applications that behave in different ways. In data centers, you may start to see more large packets. So 9,000 byte packets are particularly easier for servers to consume. They do the processing one time and then get more bandwidth. TCP/ACKs are one of the most common packets on most networks. And while these contribute a large number of packets, they're only maybe about 20 or less % of the bandwidth because they're much smaller. Most of the bandwidth is going to be in 1500 byte packets or maybe 512 byte packets, but usually it's a lot of 1500, and there's some others kind of here and there. So TCP/ACKs are going to be designed to be relatively efficient. We take the 40 bytes of TCP plus IPv4, maybe it's a bit larger if we have v6, plus some internal headers. That ends up filling a good amount of one of these block sizes for these internal transfers. So those work quite well. 1000 byte packets, 1500 byte packets, large packets, very efficient. So we're doing good here, doing good here. As I mentioned before, in a lab, you can either unintentionally with RFC2544 or intentionally, maybe if you're trying to make somebody's product look bad, create things that look less efficient. That's just part of how things work. And then I mentioned that speed up optimizes real bandwidth. And so the packets that look like they're going at 100% line rate on the test, actually internal are going above line rate. And so that extra capacity, when it's buffered with less efficient packets, smooths things out. So this is another just way of looking at what I've been talking about with speed up. And in this example, I'm taking a chip that has 8 400 gig E ports. So this would be a 3.2 terabit device. And in this case, what we have is the ports are 400 gig E, and that's then contributing to going into a 2 terabit per second bus. So this bus is faster than these. So this is the speed up. Now, if you were sending 171 byte packets through this, back with our old example, then this 2 terabits wouldn't be enough. But when you have a blend of packet sizes, lots of bandwidth with 1500 bytes, then you do have some inefficiency through this interface, but the combination of the packets working together, as well as the extra speed this interface has, is going to make everything get through. Now, it's important to note that these are not often chip level resources that we're talking about. There will be multiple of these interfaces, and so perhaps these 4 interfaces share this 2 terabits and these 4 interfaces share this 2 terabits. They're not all sharing all the chip bandwidth. So now I want to kind of take another look at what is the traffic on the internet looks like. And this one is the most recent data I can find. A lot of the data is quite old, so this is from 2023. And what we see here is that traffic around here is the 64 bytes. So you can see that by packet count, it's actually quite a large number, but by byte count, it's not too high. This is probably the 1500 byte packets, and this is probably maybe 512. I don't exactly know why there's so many large packets. It could have been that part of their network was able to carry jumbo frames where they were, collecting this data. But what you see is that, lots of the bandwidth is really happening up in this higher range. So I want to now kind of talk about how we should view this type of resource inside an ASIC. And what I would propose is that we view the PPS capacity or the bandwidth through these internal buses, just like we do any other resource. And so just as you frequently may think about, okay, how many prefixes can this chip handle? And you know that some of your routing sessions have more prefixes than others. Some of the interfaces that you use to reach those have more prefixes than others. You sort of know it kind of evens out. Similarly for PPS, you know that your different interfaces are going to have different PPS requirements. There are some pools of PPS capability within the chip that those interfaces can draw from. Similarly, bandwidth is one of these as well. We're not trying to send all 217 or all 218 byte packets through the system. We're sending a mix of data sizes through the system, and we're pulling from that bandwidth. And so we have different numbers of interfaces going to share different pools of resources, and then things are going back out. So I would encourage you to view these things that we're talking about today as just another resource. And one thing I kind of like to joke about here is that if you remember 2022, I think the best picture was called Everything Everywhere All at Once. And sometimes when I'm working with my customers, they're asking for things which seem to be like everything everywhere all at once. I need, 10 times what my router has for every single capability. And I will say that, we understand that that's a good starting point for lots of discussions, but it's really important as we work with you, if you're working with us, to figure out what do you really need. Because if we try to design to everything everywhere all at once, which in this case would be maybe line rate of 171 byte packets, we're then going to have to compromise on something else. We may have to make the device higher power. We may have to make the device have fewer prefixes. We may have to make the device larger, more difficult to cool, so higher system power. So there's lots of trade-offs that we have to make. And so I would definitely encourage you to ask for what you want, but also engage with us in these conversations so we get you, what you need plus growth versus just saying, I want everything. Because your network doesn't need everything everywhere all at once. Some of your ports are busy, some of you are not busy. Some of your routing sessions have lots of prefixes, some of them don't. And we've learned over time how to make these things work. And the issues that I'm kind of talking about today, they show up in RFC2544 tests. If you're not familiar with them, it may look like a problem, but I would say that our chips and all chips that I'm aware of, this internal bandwidth and sawtooths don't become anywhere close to a problem in real networks. Okay. So just to wrap up, the two videos we have here, RFC2544 is a good tool to learn about networks. It's important to, if you're looking at the report, to talk about every packet size, not just the 5 or 6 packet sizes that were originally posted in the RFP. Don't fear these sawtooths. They may be unexpected the first time you see them on a report, but what they're doing is they're letting us run the chip with higher bandwidth and lower power by not overbuilding that interface. Just as we don't overbuild the PPS capacity to run 64 byte packets, we don't want to overbuild the internal bandwidth capacity in a way that would cause us to be much higher power and less efficient. Okay. Be cautious out there if you see someone proposing that what's important is 212 byte packets. What they might be doing is trying to find the one that's best for them and maybe worse for their competitor. You don't have to play those games. Ask if something sort of looks different. Ask the questions. What are you trying to show me here? What does my network really need? It's important that you understand the packet size distribution in your network as part of your performance requirements. And then one more time, don't worry about it. We have plenty of capacity in the ASICs, and this is not an issue that we're having or other people are having. It's just something that looks different in a lab compared to what we used to get in the old days. Okay, thank you again for your time. Please feel free to leave a comment and we'll make sure to follow up. I hope this was useful in learning more about how high performance routers works. Thanks again.